All right, welcome everybody to the November 2024 monthly meeting of the Minnesota Astronomical Society. I am happy that you have all joined us online tonight. And if anybody showed up for the meeting at the place, I'm really sorry, but joke's on you. Okay, let me have my little slide deck. There we go. All righty. So this is our current board. I'm your president, Trina Johnson. So at least you get to see my face on the picture. VP John, Secretary Dave, Treasurer Matt, Ahmed is board member at large 1, and Jesse is board member at large 2. And I believe we are all here tonight. So that is great. Thank you for being here. And I know we have a lot to talk about and also get to our great speaker this evening. So I'll try and keep it fairly short. There's a little note from the board to all of our site leaders, just that we need to have you start really thinking and coming up that the people that haven't presented their 2025 budgets, please do so. Get those in as soon as possible because we need to start thinking about that along with the Star Party dates for next year. I know most of them have already been done and don't change very much, but for those that do or add or, remove some, get that in. I believe the deadline is December. Ahmed, when is it? December something.
Programs, it's December 1st. It's all sites, BSIG, different site
Mhm.
activities, everything. So they need to send it to me so I can organize it and make sure that there is no conflict. And then we go and update the website after we finalize everything with the board.
Okay, perfect. Thank you. And then, of course, with the membership, just wanted to let you know that we are going to be working through the budget, which is why we asked for it earlier. So that way you have the month of January to review and look at all of the budget notes instead of being overwhelmed with it in February's meeting. And then also just a notation that we do need to have February's meeting as a quorum because it is one of our 2 business meetings for the year. Our other one is the elections for the board members. Half the board switches every other year. And so we need to have a quorum of our current membership for the December meeting and for the budget meeting, business meetings. So those are our 2 official ones. So as you're thinking about the upcoming elections, even though we just had like the presidential one, but for this MAS election, we need to have you and your friends and everybody else reminded to please log in and submit your vote and see who they are. And due to the fact that we have had, we're not in our normal spot tonight, the nominations were to be delivered by midnight last night, so that way we could host and let you know who volunteered to be a nominee. So at this time, I'm going to hand it over to Ahmed for the next slide, and there's 5 or 6 slides. So Ahmed, just let me know when you want me to proceed forward, okay?
Sounds good. Thank you, Trina. And I'm not like Trina. My camera works, but I'm dressed up in my pajamas, so I'll pass on turning on the camera. Uh, Pretty much our board elections, Jesse's the one running and I'm helping her. Steve Emmerich, who is also the membership coordinator, is going to be helping us there with assigning, handing out ballots and helping people log in and registering people at the door. The key thing here is for you to be a voter, you got to be a member in good standing, and pretty much that's everybody with a specific with one exception to that, one specific member. Everyone else is a member in good standing, and then the member shall not be responsible for any financial obligation to the society. In other words, you need to be up to date on your membership dues. If you are behind on your membership dues, or they're about to expire, you can show up in person with check or cash or something, or even a screenshot that you paid it via PayPal to Steve on the door, and he will take care of it. Or even give a call and we'll let you in if you're online. And voting will be in person and electronically, as we've always done. As I said, in person if you show up, or if you join the meeting online, that would require registration. Voting by proxy is not permitted. You cannot say X in this club told me to go and vote on their behalf. That is not allowed per the bylaws. And then, last but not least, each membership is entitled to one vote per membership. So, although memberships are family memberships, only one vote per membership. So, we'll need, as Trina was saying, for the rules. Can you go back quickly here, Trina? For the rules, we need 10% quorum. So, make sure you show up. This is very important that we form quorum in order for the elections to proceed. If we do not form quorum, then we're going to need to reschedule this. So far, we've been successful every year. Let's not make this year a challenge. So, and then the other thing is quorum is established by people registering at the door or online joining the meeting. Whether they choose to abstain from voting or not voting, that's their choice. But quorum is achieved by attendance. Sounds good. And then, so you can abstain, and then only one ballot per membership, one vote per membership, and one vote per position. You cannot vote for more than one candidate. And then, for online voters specifically, registration processes, as you go in, we're going to be confirming you against the membership database. So, here quickly here for online voters, just tech support. You'll be asked to register. You'll put in your info. You'll need to go back to your email to make sure that you get in the registration information and get into the meeting. During the meeting itself, if you have any challenges and it's not working for you, you can email me. I will respond to you quickly in the meeting. I'll be watching my email, or you can call my cell phone directly in the meeting and I'll help you. The thing with my cell phone is I might be talking to someone else, helping them. So email first. I'll try to get on that fast and then call me. Sounds good. Trina, you want to go to the next slide? So yeah, in-person ones, you'll check at the desk, as I said, you'll get a ballot, you'll get a pen, you'll fill it in, and then we'll collect them as the main speaker presentation is happening. And after we've come in all of that, we're not going to collect ballots until we've confirmed that quorum has been formed. And then we'll do the counting, and then usually within a couple days, we will announce the winners. Next slide, please. And now we'll show you who the candidates are. So, first candidate for president, we have Volts. Volts, you want to talk a couple minutes? Tell us about yourself and what are your plans?
Well, they can do that, or they can do that in the December meeting. Their choice.
I'm willing to talk now, just to end in December if people want to do it. So, I've been into astronomy since I was a kid. Never really had the means to have my own telescope until I was an adult. But I really enjoyed, growing up in the city and using my binoculars and tracking the stars and planets all the time. Today, I am a mechanical engineer, and I do astrophotography as my main venture into astronomy at this point. The other thing that I do quite a bit of is restore telescopes and other astronomical instruments. Like I did my presentation several months ago about the restoration work that I did at the U of M, the observatory, and the research I did about the old Students Observatory. So I've been a patron member for MAS since about nearly about just after 2000 when I moved back to Minnesota. And I have served on the board as member at large and vice president. Member at large a couple times, vice president one term. And then the biggest achievement that Dave Faulkner and I co-chaired the Alcon convention in 2018. And according to the Astronomical League, it was one of the most successful conventions that they've ever hosted. And we also financially came out ahead. So we kept everything in the black, and we were able to put some of the extra money, surplus money, into the MAS coffers as well as the Astronomical League. So for my vision for the for being president is I think we need to keep strong and growing. We need to keep our membership numbers up and keep the flow of regular membership coming in. Another big thing that I really like to achieve is a greater percentage of volunteerism in our club. We've got over 700 members, but yet we only have several dozen members in all practicality that really step up and do a lot of jobs. We've got a lot of jobs. Some are on the board, some are, maintaining the website, some are doing membership, doing other trainings, and of course all the site committees and the volunteers that we do, volunteerism that we do at our sites and our outreach events. So the other thing I want to make sure is that we maintain a stable financial footing. I want to make sure that we follow all the Minnesota Attorney General rules and for nonprofits, and make sure that we have no issues on a legal side, and then financially we're on a positive growth spree with our incoming dues, and I fully support all of the efforts that the current board has done to investigate, what are the minimum amounts of dues needed to maintain the operations of the club, and then think about maintenance of the facilities, including Eagle Lake Observatory and all the other sites, because we do still want to grow the observatories and maintain our buildings and our infrastructure, and keep everything up to date. So the other thing, I really want to make sure that we follow our own bylaws. We pass our rules. We had several years ago. We voted. The members voted and updated the Constitution and the bylaws, and the board also put in bylaws for the sites, and I think it's very important that we maintain the integrity, that we actually follow the rules that we publish. So I think that's one of the main things. But most of all, I just want to make this club be a fun club to be part of, and I think we all enjoy it. We're all in it together for the various activities that we do. So that's kind of my campaign stump speech for it right now.
All right, wonderful. Thank you.
So next after Volts, so Volts is the only candidate for president, and on the ballot you'll get two options for each candidate. You'll get the candidates as options, and also you can choose to abstain from voting. And then for secretary we have Claire. Claire, you want to tell us a little bit about yourself and what you plan to accomplish?
So Trina kind of challenged me to do something creative like a skit. So I would speak in the December meeting, if that's okay.
Sounds good. Is it going to involve fortune cookies with astronomical predictions?
I don't know. I have to figure out something different this time, maybe.
Sounds good.
I promise to make it good.
Okay, fair enough. Okay, so yeah, by the way, the candidates will speak to the membership right before people vote. So Claire not talking today is not the end of the world. Okay, on to the next one for board member at large, Phil Ramsey. Go ahead, Phil.
Hi there. Can you hear me all right?
Yep.
Great. My name is Phil Ramsey. You probably have seen me from meetings or perhaps at other locations. I've been a member of MAS since 2018 when we moved back to Minnesota. Interested in the member at large position just to get a good start as a volunteer. I've volunteered a bit with the BSIG group, and I've recently been involved in an ad hoc team with the Eagle Lake Observatory for buildings and grounds, trying to do some troubleshooting and maintain those. You'll probably see me at CGO on a pretty regular basis, and LLCC occasionally. Let's see. let's see, I guess my background professionally is I'm an architectural specifier and actually helped design the building that we meet in.
Oh,
So,
nice.
yep, a little tidbit. I'm experienced at collaboration with teams. I'm organized. I like to get things done. I have a lot of technical skills, and I think my experience could help and benefit MAS. Short and sweet. No,
Excellent.
and no skits. Sorry.
No, that's all right. That's all
So
right.
I invite you to join me next month for that skit.
That sounds awesome. If
Right.
with you, I would do a skit.
Okay, let's do it.
All right. Awesome.
Now, thank you all. We have three great candidates. Each one of them, you know, they do a lot of work for the MES, whether in a formal capacity or have done it in a formal capacity in the past, or even currently as we speak, whether it's Vaults, Claire, or Phil. So we have three great candidates, and that's it regarding the elections. That's all those are all the candidates we have. So the key thing is next month attendance, 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 so that we can have a quorum. Thank you all.
Thank you, Ahmed. I appreciate that. Um, I just love doing these comment shots. So, all right. And then welcome to all of our new members. Hopefully there are some that are on tonight. I'm not sure. I haven't had a chance to look at all the participants, but if you are a new member and you're online, just type in the chat, say hello. We're happy to have you. We do have a great deal of people and a couple that are coming back. We're at 745 total members as of November 1st, which means that our quorum for, if it were to happen tonight, needs to be 75 people. So I know we're a little shy online for that many people, but if that many people participate and come online next month, plus or come into the building, that should be enough to match our quorum that we need to have to complete the elections for the new board and anything else that comes up. So welcome to the new members, because we love having new members, and consider volunteering because it's fun to participate in the MAS. Okay, and then in honor of Vaults and his previous moon picture, he sent me a picture of the comet. So I love that it's there, and everybody's comet pictures just look amazing. But so we'll have that for a couple of months until we go back to doing the moon, but maybe we'll keep it for a while. I don't know. You guys tell me what you think. But we do have some pretty calm month of November coming up. Our biggest meteor shower is the Leonid meteor shower that's here. And our, of course, sunrise and sunset times are changing, so we're getting a little bit more darkness, and that is wonderful. And then we're back here in back to our regular online and in-person meeting on December 5th. Just remember that's a business meeting, so hopefully everybody has a good month with some good astrophotography and some good seeing, and before we get really, really cold. So there we go. And I'm not sure if Antone is on tonight.
I am here.
Okay. I'm not sure if we didn't talk about the slide showings and stuff with your little extra, but I did put it as the next one. So
Okay.
I'm having you talk about that first, but just to let you know.
That's good. Okay, so members are able to check out one of our lunar telescopes for a month-long period. We have Dobbs and Smith Cassegrains, refractors, some binoculars, and a solar scope. Members can go to our website. Right on the home page, there's a big square box that takes you straight to the Lunarscope program, where you select the telescope you'd like to borrow, back to first, second, and third choices. And then I will receive the request, and we will make arrangements for you to pick it up at my home. We also have DVDs that's on topics.
Yeah, it's in the
Sorry?
next. That's sorry,
Oh,
that's
oh,
just in the next couple ones.
oh,
So
that's okay. Yes, we also have our great courses DVDs. And yes, and of course here, whoops,
there,
there it
now
is.
there's your DVDs. I'll go back.
There, yeah, okay. There's the DVDs. Um, with they're these are underutilized. I have them here as well. The people who have seen them said they're really very good. So if you're interested in any of these topics, you can make that request online as well. Oh, and I meant to add too that so far this year we have had 77 loans, and there are 2 more telescopes going out this weekend, and there are 2 more in the queue after that. So we are still busy.
Okay, and that's the request form. And then your special
A
announcement.
special slide, yes. I think it largely speaks for itself. Of course, it reads, member Ashley Larson married Eric Young. Among the guests was one of our Orion Dobbs. And Ashley sent me this beautiful picture of she and Eric under the Milky Way. There's really little to add to this. All I can say is congratulations again to Ashley and Eric, and we all wish you a lifetime of clear skies.
Exactly. Here. That is a gorgeous picture. Do you know where they were at?
Well, Cloverton, Minnesota.
Oh, okay. Okay. Oh yeah, that says there. Thank you. We're gonna skip ahead. Okay. And then I'm not sure if Jerry's on, but we do usually give out Astronomical League awards, and that's where I show off all the bling, and he talks about all the programs that are you can follow and you know just kind of complete as a step-by-step or trying something new, challenging yourself. But we will come back to that next month because we do have an award to hand out. And so we'll have a little bit more time at the December 5th meeting because Jerry wants to hand that out in person. So I'll skip over the rest of that tonight. Upcoming star party.
Right, Trina?
I'm sorry.
What does Jerry say in the end?
Oh, get out there and observe. I was going to skip it for tonight. Yeah. All right.
I can't.
Thank you. All right, so the upcoming star parties, we have the last one of the year at ELO. It is on Saturday, so if you can go out there and make it, that would be great. It's free and open to the public. Hopefully they'll have some clear skies at the last one. Wear warm clothes, make sure that you are able to enjoy the evening sky. There's also the last one of the year for Cedar Creek over at the East Bethel University of Minnesota site that we partnership with it through this year. And that goes from 7 to 9 this Saturday as well. The member sites, JJC is of course still open for those that have been keyholder trained out there. CGO is still open. And then LLCC, I believe, has had their last open weekend last weekend. So anything else you would have to be special and you'd have to check with the LLCC committee to do that. But otherwise we'll wait for the new calendar year next year. Which also I believe, I don't know if Clayton's on, but I believe there's still training on November 16th, but double check the forums and Slack channel to make sure that that training is still going on for November 16th for the key holdership at JJC. All right, public service announcements. We have the new member orientation that Rebecca Mezer and Steve Emmerich have worked on, and that will be at Ramsey County Library in Maplewood this coming Saturday as well. So it's a busy weekend all around. And then also, I don't know, is Rebecca or Steve on if you want to talk about it a little bit? Yep. Okay. And of course, then there's the BSIG. That is an online presentation instead of going out to Metcalf, where Ron Schmidt will be talking about how to learn about stellarium. And that is roughly right after the new member orientation, 2 different places. But and then just a special note that our longtime MAS member, I believe he was very early in the beginning. He served on the board. He's helped out immensely at ELO and several different places, has passed away. We don't have any information about a memorial or funeral services or anything yet, but as soon as we know, we will pass it on to you. I don't know, does anybody else have anything to say about Bill?
Yes, this is Thor.
Sure, thank you.
I'll mention a couple of things. I mean, as you said, Bill was a longtime member. I first met him in 1985, and he had been a member before that. But many of you will remember him as presenting reports on the total solar eclipses that he attended. And they were always just fascinating because he would include an enormous amount of information and history and, just technical information. And so anyway, I just wanted to make a few comments about it. And I made a short tribute to him because I've known him since 1985. He introduced me to the MAS, and I joined, 10 years later after that. So it's been, almost 30 years in the MAS with him. But we shared a lot in our interests of astronomy, and I even went on one of his famous solar eclipse chasing tours that took me to Kenya. And that's described in this memorial that will be published in an upcoming Gemini, I guess. But so I just wanted to sort of make sure that people acknowledge sort of his contributions, because he was a key member during many years of the MAS, and so I hope people will kind of follow along and maybe make some comments about it.
Yeah, definitely. Well, he was the one that challenged us to do find a CD for some of our funds that we had. So it took a while, but we finally did. So it's a good thing.
I'll give one last little story about Bill. Yeah, I mean, he was a brilliant man and kind of the guy in our company that we gave all the hard problems to figure out, and he was very good at it, and he had his own style, but we learned that he voted early this year, and he died just a couple of weeks ago, but the state has not been able to process his death certificate or anything like that. So it's very likely that his early vote was counted.
Oh, funny.
So if you hear any consternation about dead people voting, maybe you know someone.
That is wonderful. So yes, now we all know somebody that voted while they were dead.
And Bill would have loved it. Bill would have just loved it.
Way to go, Bill.
Yep.
This is Dave Faulkner. I knew Bill too, and I agree that his presentations on his eclipse trips were just wonderful, because he always talked about the area that he was in along with the eclipse itself. He attended the monthly meetings on a regular basis. It seemed like he was always there, and he not only advised us about the CD, but he was on the original committee that revamped the bylaws and the articles of incorporation, and was really. And I know that he was involved with building ONID. He was treasurer of the MAS for a number of years. He was really a very active, very involved member, and he will be missed. He was a great guy.
Yeah, I'll make one more comment that Bill did not have any really close family members, but I think that the members of the MAS were probably among his closest relationships.
Yeah, I would agree. I've had a lot of good relationships with the people that I know. Oh,
If I get wind of a memorial service for him in time, I'll certainly post that in the happenings so that people will know. Uh, if it comes out weekly, that's good prospect for us to be able to get information out to the membership and the people who are interested in a timely fashion. I don't
yeah,
know if I'll be able to get that information or not, but hopefully I will.
that'd be wonderful. Thank you. Thank you, Dave. Thank you, Thor. All right. Okay. And then just another little public service announcement is that it was brought to the board's attention that there is a website that was up on Cafe Press that is selling some unauthorized using our products, our logos, our information to potentially sell products that belong to the MAS. This is a store that's from the was it artist underscore 10056608. So be careful going out to there. That is not something that the board or the supports, because we have our website, which is on the left-hand side. That is this one. Where did my little stampy thing go? Anyway, that has that logo, the MAS logo, the Minnesota Astronomical Society, and you can get to it from our website, and that is with those particular URLs there. And this is what our store looks like. That once you go there, this is what it shows. So you have the MAS homepage, go down to membership, the MAS store, you can follow the QR code, go there. So if anybody is, searching around Cafe Press, finds this one on the right with the weird bubble and the MAS logo in the middle, please do not buy from them. We are working with the attorney and Cafe Press to shut it down. And if you hear about anybody doing it, let us know, because we would like to have it stopped. Thank you. And here's our store, so feel free to purchase items from there. We would love feedback on the actual store for any other particular products that you might want us to add up there. So any questions, you can let us know, and we'll be happy to answer those. And of course, Gemini articles. Father Brown is always happy to get articles from its members, as this is the only source of articles that are allowed into the Gemini is from the membership. So please write about your eclipse trip, no matter how many years ago it was, anything that you've done this summer with any trips that you've gone on, things that you've done with the kids, just any parts of it. It's wonderful to read that in the Gemini. And then also the nominations, the nominees will be published into the Gemini as well for those that are not online tonight, and to read them along with the forums and Slack later on. And those are the dates there. And as Dave notated, that the happenings that comes out once a week. If you have anything that's coming up, please let him know so that it can be published into the happenings. It's just a short little email that comes out when there's something of note, and it's very helpful for getting information out. And you can always tell him ahead of time, and he'll publish it on that particular week that it's applicable for. Which brings us to our next meeting, which is December 5th, and we'll be back in person and online. It will be our business meeting. So we need to have that quorum. This is going to be for the nominations, any other information that needs to be disseminated, we're going to put it in that meeting. And then we also have the very, very wonderful speaker that's coming up, Dr. Vanessa Bailey from the NASA Jet Propulsion Lab, talking about the Roman Space Telescope. I'm very interested in meeting her in person. can't wait. So
It's going to
thank
be
you.
online.
I'm sorry.
She's joining us online, not in person.
Oh, damn. Okay. Well, still, it'll be good to
But
hear her.
she is from Minnesota, a University of Minnesota graduate.
Oh, well, hey,
Yes.
we have a lot of good people from the University of Minnesota.
So there shouldn't be any translation issue.
No.
Yes. She side interesting story. When I started talking to her, we quickly learned she and I attended college at the University of Minnesota at the same time. We might have even taken classes together.
Oh, wow.
Yeah.
That is awesome. And of course, if you are in person next month, our after meeting gathering, which sometimes gets lost, is over at Pizza Luce in Roseville, just right off of Snelling. So we're happy to have you come out and join us in person. That way you can enjoy a little after meeting dinner. And is there any other special announcements that anybody wants to notate before we get into our feature presentation?
Yeah, Trina, this is John. I would like to.
Okay.
And this is, I forgot to send you, reach out to you to
Okay.
ask you for a slide on this. And that is at the elections next month, we're going to have one other item on the ballot. And that's going to be an amendment to our bylaws regarding the quorum. And everybody will be sending out communication because, well, according to the bylaws for an amendment, we do have to send that out to all the voting membership. And so you'll get more information on that. But basically, the bottom line on the change is to change the bylaws from requiring 10% to requiring 50 members or 10%, whichever is less. And that's following another entry in the bylaws for calling a special meeting. That's the requirement for members to call a special meeting is 50 members or 10%, whichever is less. So we're going to add that as one of the items to vote, and it's just going to be strictly a yes or no vote on that item. Have any questions on that regarding that? Okay, thank you.
All right. Thanks, John. Yeah, I forgot to put that in there. I notated it and then completely didn't do it. So thank you.
Will no vote, will abstaining count as a no?
No.
No, you don't have that option.
We don't have that option. Why?
For a bylaw,
I think you could abstain, but it's a yes or a no.
Oh, okay.
An abstain does not count as a no.
Okay.
Attending counts towards the quorum. Abstaining counts towards the quorum, but it doesn't count towards a yes or no. So you can abstain if you'd like to.
Okay. Good question. Thank you.
It doesn't count as a yes or a no, right, John?
It doesn't count as either. Only attending counts towards quorum and abstaining counts towards quorum. It does not count as a yes or a no. That's what I was saying.
That's correct.
Yes. Does that clarify the subject? Anybody has any other questions? Are we good here? I think we're good. Trina, let's move forward.
All right. Well, do you want to introduce Professor Coughlin? I'm sorry if I messed up your name.
Yeah, I'll do a quick introduction. So Professor Coughlin, he's not a stranger to this club. He's presented here before about gravitational waves and in a couple of years ago. So he knows the club, he knows the membership, he knows how we love astronomy and geek out over all this stuff. So, and he is at the Minnesota Institute of Astrophysics at the University of Minnesota. And gravitational waves is his field of research. So I'm going to hand the microphone to you, Professor. Go ahead. Thank you.
All right. Hi, folks. So yeah, I looked it up as well. So Ahmed sent me an email couple months ago, and then I looked back and I gave a talk to this group in April of 21. And so it's been a few years since we had a gravitational wave talk. Also, shout out to Anton, who's also has been joining my group for a minute now. And so for those who have, let's say, questions beyond what we do here, you should definitely talk to Anton. Yeah, so I gave this talk kind of an obnoxious title, Multi-Messenger Astrophysics Present in the Future. And so we'll, of course, the collection of folks have changed, so we'll touch a little bit on the gravitational stuff we talked about last time, but then we'll talk about what's been happening in the field over the last 3 years or so. So, and I know that it sounds like next month you're getting a talk on Roman, so you'll hear all about this forthcoming space-based infrared observatory that NASA is going to put up here. But even amongst detectors that are in existence now, this is a cool time to be doing astrophysics. And so, I'm going to give my own sort of biased perspective on kind of the current cool instrumentation, depending on who you are. So on the top left here, I have Rubin Observatory, which is a 8-meter class telescope being built down in Chile. I worked on the camera and calibration system for this thing as a graduate student, and its first light is actually in a couple of months now. And the expectation is that it'll start producing kind of public alerts for the community in a year's time, maybe a little bit longer now. And so this is exciting because it's been a long time coming, long since before I was a graduate student. Webb, which I suspect you've had many talks on Webb here, but this is a infrared observatory that's been changing all sorts of fields, whether you're doing galaxies or exoplanets or time domain astrophysics. James Webb Space Telescope, which has now been through a couple of observational cycles, it's been incredibly productive, almost no matter what field of astro that you're interested in. LIGO, Virgo, and Kagra. So we're going to be talking a fair bit about gravitational waves, but this is one area that's very close to my heart. These are kilometer scale ground-based gravitational wave detectors that mostly look for black holes and neutron stars. We'll talk about that for a bit. I also include IceCube here, which is a high energy neutrino detector down in Antarctica that it's detected neutrinos at this point from blazars from the galactic center, tidal disruption events where supermassive black holes rip apart stars. And so this is the sort of just a snapshot of the kind of awesome instruments that are out here in astrophysics. And one piece of this that excites me, so we talked, the title had multi-messenger in it, and what does that mean? We'll be talking about a science case today where you really want access to all of these instruments, and without them, you'll be missing you won't be getting the complete picture. You need the gravitational waves, you need the neutrinos, you need the optical data, you need the infrared to truly understand, in this case, how neutron star mergers work. Okay, so let's talk a little bit about gravitational waves for a bit. And so this is kind of a review from the last talk. But what does Einstein say? So we've had Einstein's theory of general relativity for more than 100 years now. And the point is, or the insight he had, was that nothing in the universe can travel faster than the speed of light, including information on the distribution of mass, right? And so what does this mean? Well, there's some kind of cosmic speed limit, but in practice then, he inferred from this that the presence of mass and equivalently energy must therefore bend the fabric of space-time. And so Einstein himself didn't actually realize, well, I will say he realized, but thought it was kind of almost a mathematical anomaly, the concept that this fabric of space-time could be wiggling in the form of gravitational waves. much less be detectable. And so it wasn't, even within his imagination that we'd actually be doing sort of fundamental astrophysics with his concept of how space-time worked. But here we are. And so how do gravitational waves work? And so this is a little movie that shows space-time that's oscillating. And so gravitational waves occur whenever you have any sudden change in the distribution of matter. And so as we move around, we produce gravitational waves. But the amplitudes of these gravitational are very, very, very small. And so when we're talking about kind of gravitational waves and how they can be detectable, we need really massive objects. And so we're thinking of things like explosions, or for example, if a star core collapses and produces some kind of supernova. Collisions, in this case, we'll be thinking about black holes and neutron stars smashing together. Rapidly spinning stars. So if I have a neutron star that's spinning and it's got some ellipticity to it, that too can produce gravitational waves. But again, you should be thinking about basically compact objects interacting with one another. And so the way that gravitational wave astronomers talk about the amplitudes of gravitational waves is in terms of strain. And so what's happening here is that as gravitational waves pass through space-time, they're expanding space in one direction and contracting space in another. And so when we talk about strain, what we're really talking about is the relative length change that I have due to a gravitational wave divided by the overall length of the sort of the measurement device. And so in a second, we'll show an image of an interferometer that's expanding and contracting. And so the length scales that we're talking about here are 4 kind of kilometer scale. In this case, for the LIGO gravitational wave detectors, it's 4 kilometers. And so, very, very large length scales. And so, I sort of mentioned Einstein was a skeptic. So how do we even know that these gravitational waves exist? Long before these ground-based interferometers existed, we've known about binary pulsar systems where you have, in this case, 2 neutron stars that are in a close orbit around one another, and radio observatories have been tracking binary pulsars for quite a while. And so the very famous example of this is the Hulse-Taylor binary pulsar. And actually, there's a professor down at Carleton, a guy by the name of Joel Weisberg, and he was a postdoc with these folks. And so we've long so when I was an undergrad down at Carleton, we've kind of long heard the story of how this worked. But if you actually track the period, or basically, how many rotations these 2 neutron stars make around one another, and you track it over time, these, according to general relativity, these pulsars should be emitting gravitational waves and therefore losing energy. So you can track basically the shift in period for these pulsars, and you get this beautiful plot here. This line is not a fit. This is an overlay of what you just get if you write down Einstein's equations and solve it for, in this case, 2 compact objects, and you see this beautiful evolution where this binary pulsar system is losing energy due to gravitational waves. And so we've known for actually quite a while that gravitational waves exist. Generally, within my community, we think of this as kind of an indirect measurement of gravitational waves. And so since then, we spent a lot of time trying to make direct detections, and we'll talk about that in a second. So how do these measurements work? And so what we have here is a basic, well, not, I should say basic, but the configuration we showed here is Michelson interferometer. And the way that interferometers work is they are highly sensitive to minute length changes in this case, the difference between these 2 arm path lengths. And so the way that this this detector works is I have a laser, I shoot it into a beam splitter, half the light goes one direction, and half the light goes orthogonal in the other direction. And the idea is that if I have two lengths, or that these two arms have the same distance, I will, when the light comes back to this beam splitter here, I will get deconstructive interference, and I will get basically no signal on my photodiode. On the other hand, if I have some kind of length difference between these two arms, then I will get light out on my photodiode. And so what's really perfect about this for studying gravitation waves is, as a gravitation wave passes through my interferometer, one arm's going to get longer, one arm's going to get shorter, and so I get kind of double the effect of this sort of path length difference. And so it's this difference in path lengths that these gravitation wave detectors are sensitive to. And as I mentioned, these days we have sort of kilometer scale detectors, and we have them around the world. And so the two LIGOs are, one is in Washington State in Hanford, Washington, and the second is in Livingston, Louisiana, not too far from Baton Rouge. In Europe, there are two detectors. So Virgo is just outside of Pisa, Italy. Geo 600, which is a 600-meter detector, and actually just less sensitive due to the fact that it's a bit smaller than these others, is outside of Hanover, Germany. And then Kagra is in a mine in Japan, not too far from Super Kamiokande, the neutrino detector. There's also, kind of on the 2030 time scale, LIGO India. And so what's kind of cool about LIGO India, it's basically a copy of the advanced LIGO detectors that we have. And so let's say with some foresight, basically spares for essentially entire detectors were constructed. And so LIGO India will be borrowing essentially all of the technology that went into the original LIGO detectors. And so for the dude who ran LIGO Livingston, Brian O'Reilly, for a while, is one of the heads of the project and is sort of flying back and forth now. And so, yeah, it's a really exciting opportunity to kind of have a third LIGO, but halfway around the world. And so a lot of what I focused on so far are ground-based gravitation wave detectors. And so the detectors, these interferometers, they're sensitive to something like 10 to 1,000 hertz, so kind of the audio band. But there's actually a big spectrum of gravitational waves, just like there's a big spectrum of electromagnetic astronomy. So you could kind of think the difference between radio astronomy or optical astronomy, or gamma ray astronomy or something like that. We have the same phenomena going on in gravitation waves these days. And so, for example, if you go down in frequency down to the millihertz band, so there's a forthcoming space mission that the European Space Agency is leading, called LISA, the Laser Interferometer Space Antenna, but you can kind of think of it as LIGO in space. And so this is a detector that will, for example, detect basically every single white dwarf binary in our galaxy. And so it's going to be inundated with gravitational waves. In LIGO land, I'll mention in a second, we've detected of order, we're, well, depending on what's public or what's not public, but of order 200, that kind of scale. Gravitational waves, whereas the day that LISA turns on, it will easily have tens of thousands of gravitational waves just there. And so it's just living in kind of a different regime. And so that's kind of a 2040 scale instrument. You go even further down the spectrum, down to kind of nanohertz, there's a group of astronomers who, just like the binary pulsar system I mentioned with this Hulse-Taylor pulsar that won the Nobel Prize, there's an entire group of astronomers who track basically the spin rotation of these neutron stars and correlate them across the sky and look for correlations in how fast they're spinning, and in particular deviations from how fast they're spinning, and assign those sort of deviations due to really low frequency gravitational waves. And so it was just a couple of years ago where these, what are known as pulsar timing arrays, they also have declared their first detection of a potential stochastic background of gravitational waves from these pulsars. And so right now they're taking more data, and the expectation is that they'll kind of improve their measurement and so on. And so the point I want to make here is that yes, life in LIGO is pretty cool, but there's all sorts of other areas of gravitational wave astronomy that are either already exploding or soon will really be coming alive. And so if I was to kind of break down the way at least I think about ground-based gravitational wave astronomy, the way that usually we think about it is if in the top row here, I have things that are well modeled, and then in the bottom row, I have things that are poorly modeled. And so by modeling here, I mean things where I know the system well enough where I can write down Einstein's equations and solve what the gravitational waves should look like, and therefore look at those, look for those systems in my data. And so in my world, in the case of relatively short or transient signals, that basically means the mergers of neutron stars and black holes. Neutron stars and black holes, despite being in some ways incredibly complicated, or in other ways incredibly simple, because you can basically model them as 2 point sources. And so when you do this problem in general relativity, it's basically like a dumbbell that's spinning, and that's the problem you're solving in gravitational waves. And so it is more complicated than that, but maybe not that much more complicated. Kind of similarly, I told you about how if I have a spinning neutron star and it's got a little ellipticity, we call them mountains, but these mountains are, of order like centimeter deviations over sort of 10-kilometer scale neutron stars. And so very, very small ellipticities that we're talking about here. That basically the gravitational waves that are emitted are twice the spin period of neutron stars. And so electromagnetically, we can track many of these neutron stars in our galaxy, and so we can search directly for the gravitational waves from them. And so that's kind of the top right-hand side of the plot. Now, on the other hand, there's all sorts of other things that we do not understand well enough to write down their gravitational waves contribution from Einstein's equations. And so kind of a quintessential example is core collapse supernovae. So if I have some very massive star and it collapses and explodes in the form of a supernova, we don't actually understand the process of that core collapse well enough to be able to write down what the gravitational waves look like. They're very messy. People can, simulate them computationally, but the truth is that between the neutrino production and everything else, we simply can't write kind of closed form models for gravitational waves like that. And so there are all sorts of searches within gravitational wave data for what we'll call unmodeled signals, but basically anything that has relatively let's say, characteristic emission that appears in all of our detectors, then looks the same in all of our detectors. And so there's entire communities who are built around kind of identifying signals like this. Now, finally, we too should have a stochastic background of gravitational waves. And so kind of there's a lot of backgrounds in astronomy. So if I'm a cosmic microwave background person, right, if I'm interested in studying kind of the fluctuations in basically in temperature and the temperature background of the universe, and people have done all sorts of cosmology and everything else with that. There's the kind of the same corollary in gravitational waves where you have contributions from black hole or neutron star mergers across the universe, supernovae across the universe, or even things like gravitational waves from the Big Bang. So kind of, let's say, non-astrophysical cosmological sources of gravitational waves. And together these sum together into this unresolvable background of gravitational waves. And that's what we call the stochastic background. And so this is kind of my overall take on kind of how people think about the astrophysics that you can do with gravitational waves. And so if I was just to sort of break down like what is the kind of science that you can do in all of these areas. And so if I was to maybe pick on a few of them, so on the top left-hand side here, in the case of neutron or black hole mergers, we can do things like test general relativity, right? I made this big deal out of the fact that we can write down Einstein's equations and then compare the expectations for the gravitational waves that are coming from these black hole mergers to what we measure. And in this way, we can constrain, was Einstein right? Right. And so this is kind of a very core thing that people do, amongst other things. And so I'll show a plot here in a second. Right. And so I've been part of LIGO since 2009 or so, and we didn't actually detect our first gravitational waves, in this case from a binary black hole merger, since until 2015. And so gravitational wave astronomy kind of as a field has only been around for less than the last 10 years or so. And so what I'm showing here is a plot of strain, which we talked about as this relative change in path length over this 4-kilometer scale detector. And so that's on the y-axis, and then on the x-axis, I have time here. And so what you see here is you have this cascading kind of sine wave of increasing frequency as the signal goes on. And so physically what's going on here is I have two black holes. They are getting closer and closer together as they're emitting gravitational waves until they eventually collide and merge and form a final larger black hole. And sort of I kind of made a big deal that you're in the audio band here. And so you can think of this as a whoop type signal, basically as these two black holes get collide and merge. And so you can kind of see that that characteristic increase in frequency in the spectrogram in the bottom plot here. Now, there's a lot of cool things that you can say about binary black hole mergers, but maybe I'll just highlight one. So a handful of years ago, I was talking to Manuela Campanelli, who's a professor at the Rochester Institute of Technology, and she's in the field that we call numerical relativity. And so there's an entire cottage industry of physicists who solve Einstein's equations on computers, and that's just what they do. And it turns out I kind of fibbed a little bit when I was saying, you just solve the dumbbell problem and you get your gravitational waves and then you're done. It is admittedly a little bit harder than that, and so to do this correctly requires both a bunch of algorithmic tricks as well as some very high-powered, high performance computing, let's say, clusters that you have to work on. And when I was talking to her and we were talking about this first detection, she was joking with me that when this top plot came through her inbox, she thought that this was just another signal that one of her graduate students had sent her, because they had solved this problem for actually many years at this point. Like, we knew what we expected binary black holes to look like from Einstein. And so what's really neat about this plot is if you in red here, if you overlay the numerical relativity signal on top of what we reconstruct the signal from our data looks like, they lie directly on top of each other. And so what's really cool about this is in some sense the ultimate theory meets experiment, right? So we have what amounts to one of the most sensitive measurements that humankind has ever made in the form of these gravitational waves. So the strain numbers you'll notice here are 10 to the minus 21. To convert strain to meaningful units, you have to multiply by 4 kilometers. But even when you multiply by 4 kilometers, you'll still get numbers that are much, much smaller than the size of an atom, right? So these are the kind of the length scales of measurements we're making. And the fit with numerical relativity, i.e. with Einstein's equations, is absolutely perfect. And so, one thing I think, to me, the coolest thing about this is you take a theory that Einstein had come up with more than 100 years before, solve that on computers in a pretty, let's say, complicated, fancy way, and then build these kilometer scale detectors and measure gravitational waves, and then boom, right? It's almost too perfect. So this is it's a really cool experiment to be a part of.
And so, question for you,
of course,
if I could. So obviously, this is a very sensitive instrument. So, do you get false positives? And if so, how do you differentiate false positives from an actual signal that you make?
Right. So, so it's absolutely true that false positives, we are fundamentally a physics experiment, and therefore measuring our background and measuring our signal is almost, everything that we do, beyond the astrophysics. And so I'll just pop back here for a second. It was realized back when sort of Ray Weiss and Kip Thorne and Barry Barish and the like, Ron Drever, all the folks who ended up winning the Nobel Prize. They realized back even 80s and 90s when they were going to go, write the NSF proposal to go build these interferometers, they were going to need more than one, right? And the idea here is that because we have this sensitive experiment, we are of course very sensitive to all sorts of things that are going on around us. And so, for example, earthquakes, magnetic fields, even, I like this one, LIGO Livingston very famously, its sensitivity goes down on Sunday mornings because people drive to church on Sundays, right? And so like we are truly sensitive to sort of humankind in all ways when it comes to these experiments. And so the advantage though we have is by creating spatially separated gravitational wave detectors, we can do basically correlation experiments. And so this does not make us immune to false positives, but it drives our false positive rate down greatly. And as you can imagine, so if you just sort of look at these bottom plots here, where you have this sort of characteristic thing that's sweeping upwards in frequency, earthquakes, magnetic fields, and such don't mask these particularly well, right? It's actually hard to construct data transients that mimic sources like this. Now, for sources like core collapse supernovae, where we don't understand them as well, it's true that we are absolutely always limited by the background that we have. So we do benefit from the multiple detectors, but indeed, measuring the false alarm rate with these searches of this kind it's entire PhDs, right, are built around this question. Yeah, so I should have said, I'm happy to take questions at any time. So if folks want to ask other things, I'm happy to. Otherwise, can move on. I can't. Yeah. Okay. I did see a chat message roll along, but since I'm in viewer mode, I can't chat. So yeah, just shout out if you need to. Okay, so as I mentioned, we've been detecting gravitational waves since 2015. We have something like 100 that are public during up to the last data run that we had going. We have, I guess we're gonna make it to something close to 300 by the end of the current set of data that we're taking now. Now, the plot that LIGO people like to show is in the top right-hand side here, where the way the plot works is you have your one compact object and your second compact object, and they add together into a third compact object. And so the blue objects here are your black holes. The orange objects are your neutron stars, which we'll talk about in a second. And so what you see here is that in general, you're having a lot of these two black holes that are paired together, making a bigger black hole. We have a number of instances of neutron stars that pair to become black holes. In yellow and red here, so yellow is the neutron stars that we know about in our galaxy and how large they are. And in red here, we have the black holes we know about in our galaxy. And these are all from electromagnetic measurements, usually people doing X-ray measurements in when you have a black hole or neutron star with some sort of stellar mass companion. And so at this point, as you can see, LIGO, or this international network of gravitational detectors, has already dwarfed the number of black holes that we know about of stellar mass within our galaxy. And so we are already the ones, after just a few relatively short years, yeah, it's been almost a decade, where we are the ones who are now dictating or kind of the mass distributions of black holes just sort of in the universe, which is pretty cool. Now, okay, so black holes are great, but I'm in the presence of a bunch of people who like to look at the sky with telescopes, and me too. I like to point telescopes at things. And so we also have a quintessential example for folks who are interested in sort of pointing telescopes at gravitational waves and their counterparts. And this happened a couple of years later in the form of GW 17817, so August of 2017, where similar to the first case, we have this sweeping set of gravitational waves, but they have happened over a much longer time scale. And so black hole mergers are only in band for less than 100 milliseconds. Neutron stars are in band for even up to a minute or minutes. And so the longer the gravitation waves, the lower the mass the system is. And so this was already pretty exciting, but even more exciting, 1.2 seconds later, after these gravitational waves arrived, then gamma rays were detected in the Fermi Gamma Ray Burst Monitor. And so there are these all-sky monitors that are searching for high energy photons. In this case, this neutron star merger was caught by some of these gamma ray burst detectors. And so the challenge of doing gravitational wave astronomy is that we don't tell you where to point with your telescope. We only tell you here is the broad part of the sky that you can look at. And so if you look in the top right-hand side here, the green here is the localization that we within the gravitational wave community provided. And then in purple, this is what the gamma ray burst folks thought where it was. And so when I say that the localization still covered 40 square degrees, many of you with your sort of 5 arc-minute imagers, me too. I too mostly work with smaller field of view imagers. This is a tough follow-up problem, right? And so it's not as simple as, here's a supernova, here's where it explodes, but you have to really go look over a large part of the sky to go find your neutron star merger. And so there are many, many teams whose whole thing is searching for these neutron star mergers. And so Ryan Foley at Santa Cruz, his team was one of the first to take an image of this particular nearby galaxy. It was about 40 megaparsecs away. And just by eye, they were looking at the images they were taking and identified a new source in this galaxy that was only 40 megaparsecs away. And subsequently, after more observations were taken, it was indeed confirmed that this was the counterpart to this neutron star merger. And this follow-up was what can only be described as one of the most, comprehensive astronomical follow-ups of anything in human history. It's been, it was clearly discovered in gravitational waves and gamma rays, but all the way from X-ray to radio, even up until recent times, it's the afterglow has been detected. And so it's been this incredible follow-up campaign. And so just to give folks a sense of, what is actually happening if I have, a neutron star merger. This is a video I took from a recent detection back from 2023 that we had. And so what you get here in this video is this is a neutron star in a black hole. And here in the colors that are showing are the gravitational waves that are being emitted as these two objects get closer and closer together. So they're losing energy as they go. And as this neutron star gets close to this black hole, it is disrupted by the black hole. And it's during the time of this disruption where you have this hot soup of neutrons, and this is going to form the signal that we're going to see. And so just to say a bit more about this, so observationally, what did I get when I found this neutron star merger? This is a spectral sequence taken at ESO at the VLT back in 2017, and so you start with a really hot, bright blue spectrum that rapidly over the course of 10 days, fades and develops features in the near infrared. And so for those of you who within this crowd who do some transients, maybe do some supernovae, and you have access, the object is up to weeks to months. This is very different. This object, came and went within a week or so. And so just to give a quick sense, so this is observationally what's going on, so kind of physically what's happening. So when I have the formation of one of these neutron star mergers, and this actually is also, you can also adopt this at least part of this picture in the case where I have a supernova where I have the collapse of one of these massive stars. You get the production of gamma rays where I have the formation of a jet of material that goes out and interacts with the surrounding, basically the surrounding material. And so this jet sort of breaks out of the cocoon of material that surrounded this neutron star merger and eventually continues onwards and goes and interacts with the interstellar medium and forms what we call an afterglow, but basically this panchromatic signal that can be detected from the optical all the way through the radio for very long time periods, even over the course of months. And we've known about that actually for even since the 90s. But the part that was a bit more special here was the formation of a kilonova. And so what is a kilonova? So Brian Metzger is a prof at Columbia University. And so he's kind of like the lead honcho theorist in our field, dude. And back in 2010, he had a paper where he defined kilonovae as the electromagnetic counterparts of compact object mergers powered by the radioactive decay of our process nuclei. And so what does that mean? And so if we just do some nuclear physics quick. So if I take just a normal seed nuclei that has protons and neutrons in it, and I introduce it into an environment that is very neutron rich, right? And so what should be clear about the environment of these neutron star mergers? You have a great excess of neutrons available to undergo nuclear interactions. And so in this particular case, when you have this environment, you have what is known as the rapid process, but basically neutrons are captured on these seed nuclei just because it is so hot. These neutrons are moving so fast that they can sort of overcome the typical strong and weak forces that govern nuclear interactions. And so now these neutron star mergers, there is why are they special? Well, it turns out that the formation of elements that are heavier than iron. So in typical supernovae, you can get sort of element formation up to kind of up to iron sizes or whatever the right word is. In this case, neutron star mergers are instead a condition where you can get the formation of quite heavy elements. And it's really governed by the fact that you have this great excess of neutrons available in these neutron star mergers. And so what's happening then is as these seed nuclei, they have neutrons that glom onto them. They're still unstable. And what happens when you have an unstable atom? Well, you have radioactive decay and you get the production of gamma rays. And so we now have this environment where we have these gamma rays that are present, and these gamma rays, they go out and interact with the surrounding material. So I have these gamma rays that are thermalizing the material around this neutron star merger, and things are getting hot. And what happens when things get hot? Well, then I get black body radiation, and so I get and if you actually kind of do out the numbers, you get right around 10,000 Kelvin in one day. And so what's happening is when people say kilonovae, so in my world, a kilonova is the optical counterpart to a neutron star merger, but what it really is I have the formation of these unstable nuclei. They're creating gamma rays. They're heating up the environment that's surrounding this neutron star merger. And I'm watching this black body radiation. And so you kind of have this reprocessed gamma ray emission in the optical and infrared. And so this is what happens when you're pointing your telescopes at these things. Okay, and so that's all well and good and be kind of interesting, but what kind of astrophysics do people care about with this stuff? And so I'll kind of posit a couple of things. So one, we study what's known as the neutron star equation of state. And so what's kind of neat is that if I'm a nuclear physicist, nuclear physics kind of breaks down at maybe 1 to 2 times nuclear saturation density. And so you can't, even just from first principles nuclear physics, we can't actually know what's going on at the very center of these neutron stars that are much, much, much denser than anything that we could ever produce here on Earth. And so, but what nuclear physics can tell us is it can make predictions about, depending on the mass of the neutron star, how big it is in terms of its radius. And so depending on the nuclear physics that's going on at the center of these neutron stars, they can tell us kind of how the mass relates to the size of the neutron star. And so if we're able to measure the mass and the radius of a neutron star in our experiment, then we can actually inform back to the nuclear physicists, what's going on at the center as these neutrons interact. And so what's really neat about these neutron star mergers, so if they have gravitational waves that are produced by them, how tidally deformable the neutron stars or how fluffy the neutron stars are actually changes the amount of or the phase of the gravitational waves that I'm getting out. And so by measuring the phase of the gravitational waves, I can tell you something about how tidally deformable the neutron stars are. Kind of similarly, and it was showed in that video, the more tidally deformable a neutron star I have, the more our process nucleosynthesis I have going on. As the neutron star gets disrupted more and more, I will produce a brighter and brighter signal. And so taken together, I'm able to make constraints on nuclear physics just from measuring properties of these neutron star mergers. Now, let's imagine that instead of a nuclear physicist, you're actually a cosmologist, right? So I imagine you are someone who is interested in how fast the universe is expanding. And so we've come to understand in the last decade or so that cosmology has a real problem. Now, what I mean by that is there are different ways to measure the expansion rate of the universe, and they disagree with one another at a very statistically significant level. And so on this plot, I have an example of the cosmic microwave background folks in the form of Planck, who are doing basically early universe measurements based on the, again, temperature fluctuations in the universe. And so that's in green here. And then in orange here, I have the type 1a supernovae people who use supernovae as standardizable candles to measure the accelerating universe. And that was given a Nobel Prize here, and even the last 20 some years, right? And so it's a pretty big deal. But these two measurements disagree. And what's unclear is if this is systematics, right? If one of these experiments do not understand kind of their experiment well enough, and so this is actually some kind of systematic error. However, both of these measurements have been done in multiple ways, all sorts of things, and there seems to be a real discrepancy here. And so this is pretty exciting because this could indicate new physics that we just simply don't understand, and we're trying to probe with astrophysics. And so the thing that's neat about gravitational waves and their counterparts, it provides yet a third way to do this measurement. And so in the background here, you'll see in blue this the measurement that we have that you can see is much, much broader than either of these measurements. But the idea here is that if you believe Einstein's theory of general relativity, I can tell you just from the gravitational waves how far away this neutron star merger was. And so in addition, I can take a spectrum and measure a redshift to the galaxy. And if I have a distance and I have a redshift, I can measure a Hubble constant or the expansion rate. And so what's neat is that it's a third where the systematic is almost completely, you have to believe, Einstein essentially. And as I said before, doing pretty good there. And so it's actually a pretty good potential measurement for us. And so we will need to get, 10, maybe 10 more of these things, depending on things, before we can get kind of a percent level measurement, but it's pretty cool. And then finally, if I only care, imagine you don't care about nuclear physics, you don't care about cosmology, you're really an astrophysicist. There are questions like, what are our process nucleosynthesis yields in these neutron star mergers? Basically, how much gold is being created in these neutron star mergers? Is it the only place where you can produce these heavy elements, or is it just one of the places? So for example, Brian Metzger's group, who I mentioned from a few slides ago, his group has a model where in certain types of supernovae and kind of in the wind surrounding the supernovae, maybe you can get heavy element formation or something. But the only way to know is to measure more of these. And so this is all well and good, right? So here's 3 different science cases. This is why you're doing this. So what's the problem? And so unfortunately, as I kind of implied with the story of 72817, there's actually a really long way to go from taking the data to getting the science out. And so if I start with my gravitational wave detector, I need to clean the data. So just like the question that was asked, how do you manage these noise transients in the data? And so we have algorithms where we try to clean the data. You need to calibrate it. So I want to be able to take the output, this photodiode signal and turn it into real units. And so I need a calibration to do that. I need to detect my gravitational waves, right? So I have this time series, and I need to be able to tell you, oh yeah, now they're just past this binary black hole merger. I need to tell you where on the sky to look, right? So I need to produce localizations for astronomers to be able to follow. I need to classify the signal. People want to know, do I have a supernova? Do I have a neutron star merger? Do I have a binary black hole merger? Do I have something else? So we need to classify the signals. And then we need to tell people. We need to produce alerts. And the green here, currently the median time is right around 30 seconds, right? So from gravitational wave strain all the way through alerts, folks, my graduate students basically, are one of the groups that kind of make this happen. And so all of this happens on very, very fast timescales and is produced for the public as quickly as possible. So once I've done this on the gravitational wave side, we've thrown these alerts over the fence to astronomers like you, right? And so there's a variety of ways folks have kind of thought about doing neutron star merger science. Perhaps you have a really wide field of view camera, right? So as I said, many of these sky maps tend to cover tens to even thousands of square degrees. And so you work on very wide field cameras to tile the sky, or perhaps you just look at galaxies in kind of our local universe. One of the plus sides of working on these gravitational wave detectors is they're only sensitive out to maybe a couple hundred megaparsecs. And so luckily, galaxy catalogs are pretty complete at that level. And so you can go around and take images at all the galaxies in our sort of local universe and look for something that's new. And both of these methods were very successful in the case of the neutron star merger in 2017. People from both, let's say, both sides of the experiments, they succeeded here. Now, once you've done all this, you'll, because you're looking over such a wide area, you're going to have all sorts of possible neutron star mergers, whereas at most only one of them can be the real thing. And in general, you're going to find a bunch of supernovae or cataclysmic variables, or maybe stars that are just flaring or anything else. As many of you know, there's a lot of things that happen in the night sky. And this is really a needle in the haystack type problem. But hopefully after you've done all this, you can identify your neutron star merger and then you can characterize it. And so as I kind of mentioned, we've been in this current data taking run, we've been running since April or maybe June of 2023. And then we will go through June or so of 2025. And so on the left-hand side here, I have this plot of, on the y-axis is distance, on the x-axis is kind of real time. And in the colors here, if I have a neutron star merger, it's in blue. A neutron star black hole merger, it's in red. A green is binary black hole. And what you'll immediately notice is a lot of green. And so we've detected a lot of binary black hole mergers. And unfortunately, not a lot of these neutron star mergers. And so the nice example I showed you, I added to this plot, but added 6 years to it. And so you notice that it was at a relatively nearby distance, and the size of these these circles, the bigger the circle, the smaller the localization you have to cover. And so, it clearly kind of stands out. But of course, people have continued to follow up, for example, these neutron star black hole mergers. And be very honest, things have not been as successful as they were, 6 years ago, 17. We haven't had any more neutron star mergers during this current data taking run. If you work out the statistics, it's like maybe a 75% chance or so to get another one during up until June of next year, essentially. But things have been overall pretty quiet. And so maybe I'll just take a few minutes here and can kind of hurry along for questions, but I'll just highlight a few things that are going on in both gravitational wave and optical astronomy land to try to help this. And so, why haven't we had neutron star mergers? Well, one is the gravitational wave events themselves, relatively low signal to noise. And so just to understand, what we're dealing with here in gravitational waves, it doesn't look like optical data. It's basically a bunch of time series. And we actually outfit these gravitational wave detectors with tens of thousands of environmental sensors and control signals and all sorts of other sort of data taking devices on site. And so this is actually a real large data science problem. And so together, I write on here, it's like 2 terabytes per day. And remember, we have 4 or 5 sites. And so actually it's quite a data challenge problem. And so, a question I often get is, how is machine learning changing this? Well, it affects, it's really making a lot of changes in the way that we do everything, all the way from interacting with these tens of thousands of sensors and measuring correlations between our gravitational wave detector and the seismometers, magnetometers, and such on site, to detecting the gravitational waves to very quickly tell me, do I have a neutron star merger or binary black hole merger present, to telling me the parameters of my neutron star merger. How big are the neutron stars? How far away they are? Machine learning is really speeding up this whole process. And I'll just highlight, one of the big changes we've had. I said that the median latency to public alerts was something like 30 seconds, and 10 to 15 of those seconds currently is just in the algorithm to detect the neutron star mergers. So here I highlight one graduate student at Minnesota, Will Benoit, and then graduate student at MIT, Ethan Marks, and together they've devised an algorithm where their headline number is down to 3 seconds, and then they can probably go even faster here. And so, and this is all using machine learning on GPUs. And so this is already really the kind of the future of this field. I also want to talk a little bit about what's going on in sort of astronomy land. And so, observationally, what makes this challenging? So kilonovae, they're hard to find. Again, for those of you who have done some supernova observations, supernovae are much brighter and they last much longer than kilonovae do. So kilonovae are subluminous. They fade very, very quickly. They also redden very fast. And so there's actually a big need not only for optical imagers, but also for near-infrared imagers, again, which has to do with the R process nucleosynthesis that's going on. And so observationally, it's actually a very challenging problem. And so we, at Minnesota, we work on an experiment called the Zwicky Transient Facility, which is a 50 square degree imager on the Palomar 1.2 meter. So Palomar is just outside of San Diego. And 50 square degrees is very useful, as we kind of talked about earlier, because we have to cover these large sky localizations. And so ZTF is actually very well matched for this problem. And so, of course, with the help, again, of, in this case, things like GPUs, I'll just highlight for a second one of the graduate students in my group so there are something like 3 billion light curves in the ZTF database. He's in the process of building a machine learning catalog to cover all 3 billion sources. And so this is useful to, for example, remove some of those contaminants in gravitational wave searches, in addition to, if you're a person who's interested in contact binaries or RLRA or what have you, he's producing, and he's produced a public catalog on Zenodo covering 300 million of those sources. So it's like 10% of the way to 3 billion. So he's on his way, but that's the kind of stuff that's going on. And of course, as I kind of let the cat out of the bag earlier, in all of this, we haven't found any more neutron star mergers since 2017. That being said, while we're doing that, we found all sorts of stuff. One thing that's pretty cool, so this was, so I'll play this little movie. I mentioned tidal disruption events earlier, where you have a black hole that's basically, you have a star that's falling into this black hole and being tidally disrupted, and this material ends up, similar to the compact binary merger case, forms a jet of material that's sent at relativistic speeds throughout the universe. Well, we found one of these in the searches for neutron star mergers, and it was the furthest one of these that had ever been found, and so on. And so what's kind of neat is, even when you're looking for kilonova, you end up finding all sorts of stuff. The other thing that I just kind of want to mention is kind of really changed in the last few years even. So we run, as part of ZTF, we run what we call the Bright Transient Survey, where in essence, for a long time, it was a bunch of graduate students and postdocs every night when ZTF would take data, would manually scan the alert stream, right? So we'd just be looking at ZTF data as it came in, and we'd take a handful of those objects, and then we would go get a spectrum of it and classify it as a supernova or what have you. Over the last few years, we've gotten, in some sense, gotten rid of the graduate students, gotten rid of the postdocs, and replaced them with machine learning and data science again, where we are at the point where we can go all the way from taking images with ZTF to requesting spectroscopy with other telescopes, and then doing classification automatically and posting these observations to the transient name server. And so last year, I highlight a graduate student at Northwestern, who's Nabil, and then kind of computational scientist at Caltech, Teofil. And as far as we know, this was the first sort of world's first completely humanless discovery of a supernova, all the way from the discovery of the supernova to getting a spectrum to posting it publicly, the whole thing. We're at something like 100 of these, and then with a very high purity. And the other thing that's pretty cool is the Swift satellite, which has, which typically, again, NASA is usually pretty careful about letting you, slew their suite of telescopes without, humans checking things. There's actually now a program where we can trigger Swift, again, without humans. And so the ZTF finds something, Swift, this UV X-ray satellite, goes and slews and gets really, really early data on mostly young supernovae. And so, again, machine learning's really, taking the cake here. So I know I got to wrap up here in a minute. I'm just gonna, there's all sorts of other things I'd love to talk about. Just sort of the other future in here, there's I mentioned ZTF, but at the very start of the talked about Rubin. Rubin's turning on next year. It's an 8-meter class telescope. It's going to have a very vibrant target of opportunity program, and it's going to really clean up in this field. And that's from the ground. And then, of course, there's space-based systems that are going to do similarly. So within our group, we work on Ultrasat and UVEX, which are both forthcoming UV imagers. And the UV sky is really nice because it's actually relatively quiet relative to the optical. And so it's actually a really good place to go looking for neutron star mergers. We've built robotic spectrographs and installed them at Kitt Peak. And actually at Minnesota, we have a 60-inch telescope where we're putting a optical and near-infrared imager to do robotic follow-up of neutron star mergers. Kind of finally, I mentioned Lisa at the very beginning. So Lisa is down in the millihertz band, and what's cool about it is that it's in this triangle configuration where LIGO is 4 kilometers. Lisa is like 20 million kilometers in terms of their the length scales, and so it's quite a it's quite an experiment. And so, as I mentioned, it'll detect all these white dwarf binaries. And here I just show an observation of the ground of one of these eclipsing white dwarf binaries that have a period of like 6.9 minutes or so. And so LISA will detect basically every single one of these in our galaxy without any trouble. Yeah, so I think I highlighted this last time, but it's worth mentioning. We have a very vibrant amateur program that we call Kilonova Catcher. We have more than 100 folks who have contributed images to the searches for gravitational waves and their counterparts worldwide. We've produced something like 2 publications a year that have citizen scientists as co-authors. This is a recent example of a pretty cool supernova from last year. And this data was completely from amateur astronomers. And so the way to get involved, just look, Google Kilonova Catcher, or just email me. But the idea here is that when we detect neutron star mergers, we clue you in and provide things like coordinates to galaxies and coordinates to interesting objects, and you can go out with your setups and go contribute. So yeah, hopefully I didn't take too much time. Big thanks for having me again. It's always nice, and yeah, happy to take any more questions. I know we're late, but yeah.
No, we're doing pretty good. There are a couple of questions. Emma, did you want to unmute and ask your questions? Or do you want me to do it?
Yeah, I can unmute.
Okay.
Some of them were partially answered, but my first question was just, you mentioned that these observations are somewhat recent, and I was wondering if that's because of improvements in detector sensitivity that made this an option, or is this something that just wasn't known to look at before, and then once it was known to look at, that's when the observations started?
Yeah, and so are we talking about the sort of the machine learning follow-up program, or are we talking about the neutron star merger program? I'm sorry.
The neutrons.
Yeah, and so basically in 2017, that was the first neutron star merger detection. We've had a couple of more neutron star merger bearing detections since, but we've only had a couple per observing run so far. And so basically, unless you, random astronomer, were involved in the last few years, you just weren't going to have an opportunity to participate. And it's true that the rate has increased, and as you kind of mentioned, it's because every observing run, the detectors have gotten better. We're kind of at this cadence where we turn on for a while, turn off for a while to increase laser power, improve the detectors, and then turn back on, and therefore the rates go up. But yeah, that's sort of, and right now we're in the data taking cycle, and after June 2025, we'll not have an opportunity to observe for another 2 years at least. We won't turn back on till 2027. So yeah, it's kind of do it now or hold your peace for at least for now. Yep.
Thanks. My other question, I think you also kind of already answered, which was just when there are new detections, is the success rate of finding and capturing them optically fairly high at this point, or could better coordination still improve this meaningfully? But it sounds like that's exactly what your Kilonova Catcher program is trying to do.
That's right. So indeed, as you can imagine, at least professional optical astronomy, very competitive, sharp-elbowed, everything like that. And so it's actually really interesting as sort of a sociological experiment to manage a situation where are my sky maps, right? I guess I may be past them, but where you do need to look over 40 square degrees, 100 square degrees, 1,000 square degrees on the sky and coordinate observations. And so of course most optical astronomers over my dead body, et cetera, et cetera. But over the last few years, between programs like Kilonova Catcher, but even just the realization amongst, let's say, professional astronomers that only one telescope can only do so much, right? You have multiple hemispheres, you have the day-night issue. And so Kilonova Catcher has been one such program to help improve the way that we do coordination. And this, of course, is targeting kind of amateur astronomers. But I mean, we use, of course, the same software stack as we use for the professionals. So, yeah, it's one big coordination problem, and that's basically what we're trying to solve.
So how well coordinated is that currently? Like with the Kilanova catcher, are you sort of distributing observation tasks out, like different observation tasks to subsets of the volunteers? So it's
Exactly
like
right.
a coordinated search?
Yeah, that's exactly right. So depending on the hemisphere and the time, yeah, for example, with the galaxy targeted stuff, depending on which hemisphere you're in, you're going to get something different. Yep. And so uh, there are ways to improve it, I would say, but we've done some of the more basic distributions that depending on who you are and where you are, you get something different. I think so it's a friend of mine who sort of controls this side of things, but I think he has kind of 10 different slices that that you can end up in somewhere. So that's kind of the order. Every uh one out of every 10 is different or whatever. Something like that.
And that's within like a given region. It's still divided up into like 10 different groups. So
This
that,
is for a given sky map.
okay,
Yeah.
cool.
Yeah.
This is very interesting. Thank you.
Mhm.
Exactly.
Oh,
Yeah, go ahead, Dean. That's what I was going to call on you.
thank you. Yeah, so I put this in the chat. Obviously, I'll just repeat it verbally, but now that you have gravitational wave observations of merging neutron stars and you're able to nail down their masses and so forth, and plus now we're starting to track down the optical and other wavelength afterglows of those. How well is anybody checking how well the luminosities in various wavelengths match the theory of our what we think is going on in a neutron star merger based on the kind of the LIGO being telling us, okay, now we know what the masses are, so we should be able to calculate the luminosities at various wavelengths.
Right. So, yeah, so there's so it kind of just like so just for everyone's context, so just kind of like I talked about this numerical relativity problem. I have Einstein's equations. I can solve what the gravitational waves look like. Um, just very similarly, I have expectations just based on things like radiative transport and, let's say quantity of ejecta, what my optical to near infrared light curve should look like, and I can kind of recover those parameters. And so actually, one of the big things my group spends time doing is exactly this, as you said, right? Take the masses of the neutron stars, predict what the amount of material that's surrounding them and going on in our process nucleosynthesis, and then translating those into observables, the light curves and the spectra and so on, and run Bayesian inference parameter estimation on them and sort of, basically check consistency. And indeed, what's neat is that there's still enough parameter space in the optical to near infrared where, as I mentioned, for example, the equation of state measurement or these tidal deformability measurements are actually quite complementary in the gravitational waves and in the optical. The optical is nice because simply the fact that you've detected a kilonova says that tidal deformability is non-zero, whereas the gravitational waves actually, on their own, even for 17.17, had like a tidal deformability measurement that was consistent with zero. I mean, it was consistent with a lot of other things, but in some sense, you sort of had this turnover between the gravitational waves and the optical data that kind of jointly allowed you to constrain this neutron star merger. And so, absolutely. Yeah, I went with 17.17. I would say the caveat to all of this is that as good as the gravitational wave expectations are, the error bars on the expectations for the kilonovae remain pretty high. People, I kind of mentioned the thermalization, how much how much do the gamma rays heat up their surrounding environment, those numbers are known only to maybe a factor of 2, just in kind of theoretically. And so there's a lot of wiggle room there. And so I actually suspect in the next maybe 10 years, as we find more of them, we're actually going to find that the observations are going to constrain sort of kilonova production. And then you'll actually be able to do this comparison that you're talking about a lot better. Because right now there's still a lot of wiggle room. Yeah.
So hopefully in a decade or so, we think we'll understand enough from this about what's happening in the kilonova to perhaps use them as standard candles now that we're accumulating a pile of observations of these objects.
Yeah, I mean, I did write a paper on this. Yeah, I think that's the I think that's the vision. I think we need. My honest take is the models are not at the point where one should be comfortable to say, look, you have some masses. I think I know what the luminosity there should be, and therefore I can measure a distance from them. However, I think as you said, in a decade you have 10 or even more of these things, and you've really pinned down like this thermalization problem and like even kind of the production of these R process elements and the line profiles they have and so on. Then I think we're doing cosmology with kilonovae. Yeah, so but it's that time scale. Yeah.
We can look forward to resolving the Hubble tension then, right?
That's right. Yep.
Thank you.
Thank you.
Excellent. Are there any other questions? I didn't see any more in the chat, but if you have any online, just gonna unmute and let us know. All right. Well, thank you very much, Michael. I appreciate that. And always looking forward to your next presentation and more information as it comes out with the gravitational waves and anything else that science has to offer us.
Thanks all for having me. It was really nice.
All right. Wonderful. Wonderful. All right. Well, that concludes our meeting for tonight. Everybody have a great night, and we'll see you on December 5th. Remind your friends and fellow astronomers to join us at the meeting, online or in person, so we get our quorum and get our new board elected. All right. Thank you. Have a good night.